All right, up next we have Howard. All right, welcome to the live stream, Howard. We've got some zero knowledge going on. Is that what we're going to discuss today?
Yeah. And first, I just want to say thank you for having me on here. I'm very excited to be here.
Excellent. It's our privilege. All right, take it away.
All right, so let's get started. So I'm Howard, and today I want to talk a little bit about some of the technology that we're building at Aleo. As a high-level overview, first I want to just say, this has been a project that we've been working on for many years now. It actually started off as a research project about 4 years ago, and at the time with my co-authors, we were looking at the blockchain ecosystem and evaluating the technology out there. There was really two verticals to evaluate on. We found that there's programmability and privacy. As most of you know, Bitcoin is quite low on both. Ethereum had went one direction to offer high programmability, and Zcash went the other to offer high privacy. But there was this upper right-hand quadrant of high programmability and high privacy, where there just wasn't a solution available. And it wasn't for a lack of trying. People were definitely coming up with different approaches, but they all made different trade-offs, whether it be using trusted hardware or potentially having large compromises on crypto economic security. And because of that, we kind of set out for ourselves to say, could we devise a protocol that could be not only offer high privacy and high programmability, but have minimal trust assumptions, primarily just on basically pure math. And what we've built is actually a system which hopefully will create some intrigue that allows for effectively zero gas fees as a requirement, and also unlimited application runtimes. And I'll get into a little bit more on that in just a second. But with that work that we did, we basically designed a new system called ZEXI. ZEXI stands for Zero Knowledge Executions, and it is a new model for doing decentralized computations. Fundamentally, ZEXI can be broken down into three parts. There is the setup, the prover, and the verifier. And with the setup, it's a one-time setup, in this case, a universal setup. And what that means is that at the genesis of a system like this, all participants, the idea is how everybody, as part of just getting the system up and running, participate in an MPC that will then create entropy or randomness that is then used to seed a proving key and verification key for every application in the system. From there, provers execute the application, and provers are naturally motivated in the sense that they take in some program, they take in these proving keys, and they provide and produce a state transition. And lastly, this then gets bundled into something called the zero knowledge proof, which verifiers can quickly check. And one thing that I want to call out is with a system like this, just as Bitcoin can't run the EVM, Ethereum can't execute ZEXI, or to the extent that people have tried to bake it in, it's really hard to get all of the benefits of a system like this on Ethereum. And so because of that, we've designed a new system called Aleo, which introduces zero knowledge executions for decentralized systems. And the way that we think about it, or like to think about it, is to break it into three parts. There's write, run, and deploy. And for application developers, the idea is to start in this programming language that we've been working on called Leo. Leo looks and feels a lot like JavaScript or TypeScript. And under the hood, what it actually does is it will compile that down into something called a zero knowledge circuit. A zero knowledge circuit itself is effectively a representation of that high level program that the developer defined. And it comes with these proving keys and verification key that is then used for execution. So once the developer has written their application, they can then ship it off to provers. And provers, as I had just mentioned, their job is to take in this code along with some input and execute a state transition, which is then encapsulated into a transaction. That transaction is then broadcast to an open network, in this case, blockchain, which can be quickly verified. Because the transaction itself is represented with a zero knowledge proof, we actually get transactions that are constant time and constant size, which is quite remarkable, but also convenient for many reasons. And I'd like to talk a little bit about the properties of this now. So first, with a system like this, we've built something that's really good for speed. And what I mean by that is this model allows for applications to run once and once only. there's no miner re-execution, unlike existing smart contract platforms, which have to re-execute every single state transition, for the remainder of time to verify the integrity of the ledger. And because of every transaction itself is very concise, it's constant time and constant size to check, we can then pack a lot of transactions into blocks, and just by virtue of that, we can have a very high throughput. The second point to make about it is that with a design like this, it really creates a system for integrity. Unlike existing solutions where there are trade-offs on crypto economic security, Aleo has no compromise on computational integrity. The idea is that instead of having crypto economic security, you have cryptographic security. And more so, because of the design of off-chain executions in this model, users actually get to control their data. They get to own their logic, and we don't compromise on that. And because every transaction then is private, this allows for effectively zero MEV. So in the mempool, miners have no advantage other than by random chance to try to game a system like this. And I think that this is something that is very valuable for DeFi protocols that are coming out today. But the last point to really call out is just this idea of scale. In canonical layer one thinking, scale is usually about TPS. And this is where I'd like to try to call out something that's a little bit different, which is to say scalability in the runtime of an application. On existing smart contract platforms, everyone has to timeshare a global computer. And because of that, everybody is fighting or competing to effectively get this 100 millisecond runtime of their application. And by just by that property alone, it really limits the flexibility or expressivity of applications that you can run. With a model like this, applications can run off-chain verifiably. And so because of that, we get unlimited application runtimes. What I mean by that is, instead of being bounded by that 100 milliseconds, you can now run an application that takes a second, maybe a minute, an hour, half a day, you name it. And because everything is represented as a zero-knowledge proof here, those transactions themselves still are very succinct, about a kilobyte in size. And so because of that, this allows for far more expressivity in applications, and it lets you do things that just aren't possible on existing systems. For example, people talk all the time about having bonding curves, and bonding curves usually have to be hard-coded and fixed. But what if, for example, we could have a dynamic bonding curve via linear regression? You take the last 100 trades, you plot them, and then you basically do regression to find the tangent for where the bonding curve should lie. There's far more applications which take multiple seconds in this case to run that just simply aren't gas efficient. And so because of this design, we're able to support new types of applications, and certainly take DeFi in directions that just don't exist currently. But one thing that I really want to call out, especially as a workshop, is that we've been working on a product called Aleo Studio, which is an IDE for writing zero-knowledge applications. And Aleo Studio itself is a batteries included one-stop shop solution for writing these types of applications that I'm describing. It has Leo baked in. We're currently working on getting a package manager built into it, and also getting light clients integrated into it. And I'd like to show you Aleo Studio firsthand now, to give you a taste for an example application, and to walk you through how it works. So over here is Aleo Studio. It's open, and I have a simple roulette example in front of us. In this example, I want to call out this function, the main function. For every Leo application, the main function is the entry point in, and it takes as input user-defined parameters. Oops, sorry about that. It takes as input user-defined parameters, and it outputs user-defined state. In this case, because the application is roulette, let's walk through how this executes. We start by defining a struct called roulette, and you can see there's a roulette.leo here, which itself encodes some logic we will get to in a second. Going back to this main function, this initializes the roulette table.
Excuse me, Howard. Could you increase the text size for us so we can read?
Yeah, absolutely.
Excellent. Thank you very much. Maybe one more?
Yep.
Great.
How's that? Awesome. So we start by initializing a roulette table. And the next step here is, because this is a round of roulette for a specific player, we want to encode the player into this round. And so we take the player's address, which is passed in as input, and convert it to bytes so that we have this participant encoded in bytes. And next, we take the round parameters. So there is a round number that's passed in. In this case, this is the round of roulette that we're playing. So maybe it's the 5th spin of the wheel or the 20th spin of the wheel. That's this number. We also encode the player again as well in here, along with the bet, the specific bet that the player is making, and a bet amount. And these are things that we're then using in an encode function. And if I scroll up here, you can see that all I'm really doing is actually just encoding these into byte arrays. So we return effectively just arrays of bytes. And the reason for this, as you'll see in this next step, is that we're going to use it to evaluate. So once we've encoded this data into these two variables, which we call the seed and the data, we then start to use this. And so we pass this into an evaluate function, which in this case calls Blake2s. The idea, as many of you have probably seen, is that verifiable randomness in decentralized applications is very difficult to achieve natively. And certainly there's been many attempts at getting random beacons up and certainly VRF services that are through oracles. In this case, because everything is executing in a zero-knowledge proof, we have verifiability for free effectively. And what we need now is a good randomness. And so we're using, in this case, a pseudo-random function, Blake2s, to evaluate on the seed and data some output. This output we call a digest. And in this case, we encode it as a variable called round hash. So now that we have this round hash, which represents this state, the deterministic verifiable randomness state for this roulette spin, we can now pass it in along with the bet data. And now let's go back to that roulette struct to see how the spin works. So if I open up roulette.leo, you can see here that we have this spin function, which takes as input the round hash, the bet type, and the bet amount. The first thing we want to do is use the round hash to determine where the ball landed on the wheel. And so it's a simple operation where we basically just encode it and check to see out of 37 for European roulette what the number is. Once we have the number, we do a console.log, which I'll talk a little bit more about in a second. But this allows us to print out where we've landed on the wheel. So this will say we landed on some number. And the next step, of course, is to figure out, did we win anything from this, right? So we made a bet. We want to know whether this is a winning bet. And so this is some logic to check for the different cases. And up here in the comments, I actually just quickly made a note of the 4 different types of betting styles that this example gives, which is to bet on a modulus, to bet on 0, basically, to bet on a specific number, to bet on a dozen, or to bet 18s. And so this logic here basically checks whether you've won. And once you have that, the next step is to say, if you did win, what is the expected payout? And so, of course, with a roulette table, there are different payouts for different types of bets. Some are 2-to-1, some are 36-to-1, some are 3-to-1, or 2-to-1. And in this case, we can calculate what that payout would look like. And so we return basically a variable, which is a Boolean that says whether you won or not. In addition, it returns the payout, which is how much you won if you did win. And so if we go back to our main function again, we can see that spin outputs basically is winner and amount. And now we want to print the result. So the first thing to check is, did we win? If we did, let's print out this amount that came out of that spin and say you won this amount of tokens, and encode that into the outcome. Or if you lost, then we want to return the bet amount, not the payout amount, but the bet amount in this case, and encode that into the outcome. And finally, we have this return method, which will now return the round number +1, since we've now spun the wheel one more time, along with the player's data, whether they won or not, and that outcome. And so with that, I want to run this main function so you can see it in action for yourself. So I'm going to hit this play button up here in the upper right-hand corner. And if you just give it a second, it will effectively execute. And you can see here, it says compiling the main program. It landed on 13. You won 36 tokens and complete. Now you may be wondering, where did this 13 come from and why did we win 36? So this gets into a concept of input and output state. So remember that I had mentioned here with the main function that there are inputs we take in and execute the state transition on, which are then encoded into the output. So where does this input state come from? Well, in the Zexi model, everything is encoded in something called records. So records define the state, the payload effectively of that application. And those records are executing in the state transition that you're seeing here. If we go to the inputs folder here, you can see that there's actually there's two files here. There's roulette.in and roulette.state. Roulette.in is actually this input file, which is an encoding of the payload in that record. And in this case, the record has with it the round number, which is 15, the player, and this is their address. The bet was on the number 13. The bet type was 1, which means they're actually betting on the number 1. And the amount that they were betting was also 1. And so with that, the reason why this result was that you won 36 tokens is because you landed on 13, you had chosen 13, and because you had bet on that specific number, it's a 36-to-1 payout, and so you won 36 tokens. That's the idea. One other thing that I want to call out, which is I think quite interesting or unique, is this idea of unit tests and integration tests. Unlike other DSLs that we've seen out there, we have yet to see a really good framework from other DSLs for effectively writing zero-knowledge applications with testing. And so we've made unit testing a huge priority in this language. And actually, in this case, we have a test roulette function that looks very similar to this main function. And the point being is to highlight that it can replicate the same type of logic that a main function can in the language natively. Unlike the main function, though, the final output is a little bit different. Instead of returning the outcome, we're actually doing some assertion checks. In this case, console.assert on the winner and console.assert on the amount. And so I'm going to run this for y'all so you can see the test case. And as it's executing, I also want to just discuss a little bit about this idea of console. So as you can see, the console has said the winner case here is true. The amount is 36, and it also is correct, and therefore the test returned OK, meaning it succeeded. Now, console is actually a unique keyword in the Leo programming language, and the reason that we have this keyword is because unlike in traditional programming languages, Leo is compiling on a high level this language down into something called a circuit. The circuit itself has to be generic and flexible for use for effectively the remainder of time in a system like this on a blockchain. And those consoles are primarily executed only at compile time. And so this is an easy way for developers to debug, to quickly assert that the state of things is behaving that they want, but not encoded into the final circuit if they don't want it to be. Certainly they can write assertion statements. There's nothing that prevents them from writing assert statements in the native form. But whenever the keyword console is used, that means that this is only during compile time, or effectively the developer's development time, that they're using this to evaluate and to sanity check that the application is behaving correctly. If they wanted to do actual asserts, they could simply write a very simple function assert and basically define A and B and pass it in and check that these cases equal. This is actually something that we're looking to add into the language very soon ourselves. But the point being is that console is something that allows for a compile time check rather than an execution time check. And with that, I also want to call out the outputs file. So as I mentioned in this main function, once you take in some input, it executes, and then we output some state. What happens to that state? Well, that state actually outputs, for one, effectively a proof about this execution to say that it was correct. And in addition, it outputs the circuit that represents this program so that it can be deployed to the blockchain. These are pieces that currently reason basically from the in and out files that I've described, for example, this in, and those are records themselves that live on chain. And so, in the current form, as you see here, this is actually encoded in a record that lives on chain, and that's something that we're taking down and then executing and then putting back on chain in the form of a transaction. And this is the state transition that we're talking about. So this gives you a high level on one example, which is roulette. Hopefully it helps to elucidate some of the potential use cases or applications beyond here. In this case, having effectively a VRF in a system like this without having to go to some third-party oracle or to go to some external system, and to have very good transparency on how it works, is a huge value add that just is very difficult to replicate on existing smart contract systems. And so with that, I want to open up to Q&A, or if there's anyone who's interested to ask specific questions, I'm happy to answer as well.
Excellent. Thank you, Howard. Let me just double check in here. Let me get into the comments.
Sure.
I can pull that off for you. If you guys have questions for Howard, got some compliments for the talk. Excellent, from Sturkey. Cool. A question maybe to extend on kind of what you were talking about with the VRFs. What are some other use cases beyond gaming and things like that that you guys have explored?
Yeah, so there's actually a really interesting like domain of specifically for DeFi that I think is really underexplored right now. With a system like this, you can build applications that just aren't possible on Ethereum today. For example, dark pools or really effective mixers. And what I mean by that is that because everything is public on a system like Ethereum, those smart contracts aren't actually hiding or able to shield any of the data or orders that are open in an exchange. And so in this context, it's really easy to build dark pools that can be used for either OTC trades or just for dark pool trading on its own. But in addition, it's also great for shielded wallets because applications on-chain themselves encode state in an encrypted form. And so because of that, it's easy to basically shield your assets on a system like this. I'd say kind of a third area that beyond gaming and DeFi that's interesting is interoperability. I know people have talked a lot about interoperability over the past few years, but it's primarily been very much kind of closed ecosystems in the sense that you have a hub and spoke model for a new ecosystem. Because zero knowledge proofs themselves are chain agnostic, they can reason about the state of other chains and effectively transfer state from one chain to another. And this is a nice way of encoding state so that, for example, if I wanted to lock tokens in a smart contract on Ethereum with a commitment, I could give a zero knowledge proof on Aleo that I know the pre-image to a commitment for a transaction where I locked up an ERC20 token over there and unlock it over here, a virtual equivalent. That's a two-way bridge in this case that lets you move seamlessly between systems. And so that's kind of a third area where I think for value transfer or for helping other L1s get exposure to the DeFi on Ethereum or to bring assets, other L1 assets over to Ethereum's DeFi ecosystem, this is a natural way of doing bridging as well. And so those are kind of the three areas that I think are quite promising.
Yeah, cool. Looks like somebody's asking about if there's limitations transaction per second.
Yeah, it's a great question. So basically, every transaction has to be verified. So every transaction itself is a zero knowledge proof, and it has to be verified. It takes about 10 milliseconds to check that proof. And so the limitation is really on like basically just CPU bounds, like how quickly you can execute the verification and how quickly you can pack as many transactions into a block as possible. The real limitations here aren't on re-execution, unlike in the Ethereum model, because miners don't have to re-execute. By the time the transaction has already reached the mempool, it's already been executed, and the proof gives an attestation saying that the outcome of that state transition was correct. And so, the only limitation to TPS is really your hardware.
Excellent. I'm not sure, this doesn't mean much to me, but I'd let you interpret that.
Sure. Yeah. Is this related to the nipple pals? Yeah. So this is related to nipple pals, and like there's also like with James Prestwich's work on like ZK rollouts. These are concepts that we've been exploring quite a bit because it basically allows you to start to bundle state using a zero knowledge proof and send it over to another chain. So for example, I could on Aleo take the past let's say the past 20 blocks and then check the proof in each of those 20 blocks into one single proof, which I then send off to Ethereum in a smart contract, and in Ethereum smart contract, verify that proof, which then validates that a transaction in the latest block, for example, has had 20 block confirmations on Aleo, and that could be a nice way to basically translate state or transfer state from one system to another. And as you can probably imagine, it's not just limited to tokens, but it's limited, but it can be extensible to arbitrary types of data beyond just tokens.
Yeah. Here's one. He says, how do you handle circuit versioning within high-level language?
Yeah, Strad, thanks for asking that one. It's a very good question. This is actually one of the hardest or harder parts of our discussions in terms of developing Leo. So effectively, the way that we've been thinking about it currently is to have 3 formats. There's basically, on a high level, the Leo code that you've written. There is then effectively an intermediate representation that we're currently working on. That intermediate representation is what we would host on a package manager. And the rationale, well, I'll get to the rationale for that in a second, but finally then you have the R1CS circuit itself, which is what's persisted in an on-chain circuit registry. And going back to the IR itself is intended for composability, so that on a package manager, the idea is if you do versioning, the IR is where you basically mux to a new version, but it's also a way for you to do inter-contract calls. And so you can compose different pieces together in this IR and basically compose new types of applications from that. And the idea here is to minimize the amount of bloat on chain for like circuits that you would want to represent. Yeah, like that's something that we've been actually having quite a bit of open discussion for designing. Would love to chat with you about it. With regards to then what's then encoded on chain, basically what you deploy on there is the final version. And if you want a new version, you basically can, in the same way as on Ethereum with proxy contracts, have basically a proxy option where if you're like a contract.owner, you can authorize spending the death program for a record, either from the current circuit or some owner-defined new circuit, predicate ID, basically. So that's the high level on that. Hopefully that gives some context there.
Yeah, hopefully. Excellent. We've got one here from Radio Operator, says they love the approach. Are there validators?
So I guess if validators are in the context of like proof, or is it like proof of stake validators?
Yeah, well, I'm not super sure.
I'll attempt to answer. Hopefully, it's the right one. But basically, like the system itself is a proof of work based system, and so we use miners in this case. And actually, you may be wondering why. The rationale is that we're devising a consensus mechanism called proof of succinct work, and the goal is just like in Bitcoin, where you grind SHA-256 to basically find a solution and then get a block reward. We actually are grinding snarks and then using that to then incentivize miners with a block reward. And the goal personally is to actually develop specialized hardware for zero knowledge proof generation and incentivize miners to develop that. Since as many of you know, zero knowledge has only become really practical for small to mid-sized applications in the past 2 to 3 years. The goal is to really continue to push those boundaries, to have people start looking at GPUs, FPGAs, ASICs, and get us to basically 100x performance improvements for ZK. One way to do it, and the best way that we know how to do it, is effectively with miners, basically incentivizing miners to do that. And so we've built a consensus algorithm that is proof of work based, and instead of grinding SHA-256, you grind snarks in this case. I'd also like to call out one other point to that, which is that that's the miner side of it, but there's also the prover side to things, which is with provers, we want to give the ability for anyone to be also a facilitator of executing state transitions. So, there is in Zexy a section that we call delegable DPC. And the idea is that with delegable DPC is that you can delegate your execution to trustlessly to a third party, and they can't cheat because, well, either they execute the state transition correctly for you and give you a zero knowledge proof back attesting to it, or nothing happens at all. And so with the delegable model, this opens up another avenue where one can be both a miner and a prover, and they're not mutually exclusive. And this gives different avenues for people to actually be involved with their hardware.
Cool. One last question, I think, before we have to transition. But if we want to learn more about zero knowledge, what would you recommend to learn?
Yeah, well, first off, I'd give a huge shout out to the Zero Knowledge podcast. There's a lot of wonderful material there to learn about the different approaches people have taken. In terms of the primitives and the cryptography that we're using for Aleo, I would highly recommend checking out developer.aleo.org, which is where our developer documentation is. It gives a high-level overview on how to conceptualize this model that we've been building, but also to just get started on writing your first Leo application in this case. And so developer.aleo.org is that link. If you want to start programming in the studio that you just saw, the link to download that is aleo.studio.
Great. Thank you very much, Howard. Here's John as well.
No, thank you. Really appreciate it.
Howard, awesome presentation. Thanks, man. We appreciate it.
Yeah, no, thank you for having me. This was awesome.
No problem at all, man. Have a good night. Are you going to play chess?
Sorry?
Are you playing chess?
I'm not playing chess at the moment, but maybe.
No, the tournament tonight. We have an ETHDenver tournament happening right now.
Oh,
I gotta go. So I gotta go play some chess with. I gotta go beat Iwaki on all of this. So anyway, thank you, Howard. We really appreciate it.
Yeah, no, thank you. Thank you for having me.
You got it.
All right, take care.